So for a 3 by 3, we could end up with 1, 2, or 3 eigenvalues. Right? Depends on how it factors. So if you have 3, then you have to row reduce 3 separate matrices to find the eigenspace. So it's a little bit longer. So these numbers don't look nice, but I worked this out before and it did work out okay. So we'll try it. So step 1 is to find a minus lambda I, which, remember, is just subtracting lambda down the main diagonal. Spread it out a little bit so that you can still see the rows. Okay. Now we have to do the determinant of that. So we just did a whole section on determinant, and there was things with row reductions that make zeros first to make it easier. Now these have, so you'll want to do that unless the vector or the matrix already has a bunch of zeros. You'll probably want to make a couple zeros at least. Even 1 makes it a little better. Do you see a row reduction that we could do on this that would make a 0 right away? You don't have to have 1s and 0s in the right places. That's not a rule. So where could we do one? Do you see these are plus 4 and a minus 4? What does adding 2 rows together, or replacing a row with what does that do to the determinant? It does nothing, right? It stays the same. So we could do some row reductions here. So we need to find the determinant. Not nice with these numbers, although we could do it. It would be better to get some zeros. The other benefit of getting some zeros and not doing this out a long way is that the polynomial will be easier to factor. You may not need to use a polynomial long division or synthetic division if you make some zeros first. Okay? So, use row reductions to make it easier. So let's do row 2 is row 3 plus row 2. That has no effect. So this has no change. What does have a change on the determinant? When you multiply or divide a row by a member, or if you switch rows around. Okay? But if we just do these type of row operations, the determinant stays the same. So what will happen if we leave row 1 alone? We're going to replace row 2 with these added together. So that will be a 0. This plus this, 1 minus lambda minus 4, minus lambda minus 3. And then 8 minus 11 minus lambda. Same thing. Okay, so this still has the same determinant. Now, what if we wanted to make this 4 into a 0 as well? It might be too tricky, because what would you have to do? So to make this a 0, you have to use the other row that's here. You would have to first make that into a 1 by dividing the row by 5 minus lambda. You don't really want to do that. Then you have to divide everything by 5 minus lambda. You've got fractions with lambdas in the denominator, right? It's not really worth it. So you can see, like, you don't really want to change this row at all because we just made a 0. But sometimes one of these, adding these two together, might make another 0 somewhere. Is there a way we could do that?
So if you did row 1.
Okay.
Plus 2 times row 2.
Right. So leave this one alone because we made the 0. If you now use that or change that, you might lose the 0 you just made. But if we look at these two rows, and there's something that's not too hard, a row reduction, multiply one of them by something and add it to the other one to make another 0, then I would do that. So if you look at these two numbers, if we multiply this by 2 and add them together, it could replace either row, it doesn't matter which one. The other one stays the same though. So you multiply this by 2 and add it together, and that would give us our new, say, row 1, then we would have another 0. So the question is, which one do you want the 0 in, here or here? I would want it in the, it actually would make 0 difference. It makes no difference. I would probably put it in the top one, because when you're going down, that would hit 0 twice doing your determinant, but backwards it won't. If you put it here, backwards it'll hit it the 0 twice, so it really actually doesn't matter. So let's say we are replacing row 1 with 2 times row 3, because that will make that a negative 8, plus row 1. Does that step make sense? So 2 times row 3, two times 11, and 2 times lambda, plus row 1, add them together. Here we will have minus 3 minus lambda, 0, and here, seeing a lot of the similar numbers, okay? Which is fine, because we're supposed to have infinitely many solutions, so the numbers are going to have to match up later anyway. Okay, so let's replace that. So that is our new row 1. Row 2, and row. Now, it would be nice to have these as positive, but remember, if you change the sign, that's like multiplying by -1, you'd then have to multiply the determinant by -1. You don't really want to get into doing things like that, in case you forgot. So we've made a couple zeros. This makes the determinant a bit easier, like significantly, because when you do your, if some of them disappear, or some calculations you don't have to find, especially with a lambda in there, it's much, much easier. Even if you just make 1 0 better, I try to make them actually work out nice.
So if you row 1 equals 2 times row 2.
Oh yeah, so
You have another 0.
let's see. Okay, let's see. So you're saying if we do what?
So row 1 will equal 2 times row 2 plus row 1.
So then one of these will be a 0?
Yeah.
But then the other one will not be a 0 anymore. Do you see? Yeah. We've used like both sets, and we made a 0 here and here, so we don't really want to use either of these to change that one. Because then you end up losing a 0. Like, yeah. I mean, you could use one of these to change that, if you left these the same, but you don't want to use these two together, because as soon as you add these together, you lose the 0 that you made in that row. Yeah, you'll see. If you did it and you said, oh, I can make another 0, and then you say, shoot, I still only have 2 zeros. What happened, right? Okay, so let's go with this. What row or column do we want to do for the determinant, or do we just want to do this method, the diagonals? Or we could do Laplace along one row or column. What's everyone's choice? So we need the determinant of this. Well, let's just go along the diagonals. So our first main diagonal is minus 3 minus lambda times minus lambda minus 3 times minus 11 minus lambda. So that's our main diagonal. Still going forward, 0 and another 0. So that's good. That's going forward, right? Because we're going to hit the 0 and we're going to hit the 0 on the other one. All right, so then what? Going backwards. We're not going to hit the zeros as many times. So going backwards, we've got our main diagonal. Right? And then our off diagonals. So 0, 0 with this, that's 0. And then our other one, minus lambda minus lambda minus 3 and minus 4. Okay. So I'm just going to change the signs, just change the order of these a little bit. How could you fix up this term right here without multiplying anything out? Don't FOIL anything out, and this is what I'm saying. You could FOIL it all out and get a polynomial, but then you have to do synthetic division or polynomial long division. I'm going to show you how you can not do that, okay, for most questions. As long as you've made a couple zeros and have a bunch of factors that are similar, it will work. Are these two the same? Yeah. So we could say this is minus lambda minus 3 squared times minus 11 minus lambda. Do you agree with that?
Yeah.
Okay. Here, minus and a minus is a plus 4. And if we put that minus in here, what could we write this one as? So I could change that to a minus, but there is a 4 there. So this could still be plus 4. Oh, and, okay. Can I fix this up any more? So well, all I did here is get rid of that bracket. 4, what is this? 2 times minus lambda minus, or minus 3 minus lambda? Oh, lambda's weird. But if I factor out a 2, it's another one of these. So what could I change the 4 to? 8. Minus lambda minus 3 and another minus lambda minus 3. And here, now I still didn't FOIL anything out, but do you notice that they all have that same term in it? And both, 2 of them squared. So you can actually do a common factor here and factor that out. So if we factor out minus lambda minus 3 squared, what do we have left? Minus lambda, or minus 11 minus lambda, plus 8, plus 4. You have to practice these. What does this work out to be? 12 minus 11 is 1. All right, so factored, our characteristic polynomial, even though we're not writing it as a polynomial, polynomial is this, and I didn't have to use long division. Okay, but this took a long time to get to this point, mostly because I was talking a lot. But what did we do? We subtracted lambdas from the diagonal. Then we have to do the determinant. If you don't make zeros, you won't be able to do this, factoring out common factors all along. You'll have to be able to do polynomial long division, because you'll have all these terms and they will not have something in common to factor out to the front. If you make zeros, a couple zeros, this will always sort of work out nice that you can do a common factor and pull it out to the front without doing the long division. Okay? If you end up with terms that don't have these common factors, then you would have to do long division to get your answers. So what are the eigenvalues? So minus lambda minus 3 squared times 1 minus lambda equals 0. So this one, so lambda is minus 3, and this one, so we could say lambda 1 is negative 3 and lambda 2 is 1, or vice versa. So they'll usually put a little subscript so that you can identify which was which, but it doesn't really matter. There's two different lambda values. One is negative 3 and one is positive 1. Okay? So what do we do with those? We plug them back into A minus lambda I row reduce. The row reduction, though, is always easy because 2 rows will work out nice. There'll be a row of zeros. Okay, so for lambda is negative 3. Plug negative 3 in. Minus 8. Augment it with zeros and row reduce. But do you see what happens? This one is nice because 2 rows are going to be zeros because all 3 of the rows are multiple of each other. Yeah. So can we row reduce this without actually writing down a whole bunch of operations? Yeah, you sure can. So like you need to divide 1 by, but then these are a multiple of that. They're going to be all zeros. So I usually jump right and put this RREF. I usually jump right to the answer when I do them, but you can do the whole row reduction. It really is not many steps because you end up with rows of zeros right away. So you can go through making the 1, then use the 1 to make the zeros. You can go through all of that. Here, if we divide that by 8, and then if we end up using that to get rid of these will both be rows of zeros. But again, just do the row reduction if you're not sure how to jump right to the answer. Okay. So here's our row reduction. So this is X, Y, Z. Which ones are free? Both Y and Z are free because there's only one lead 1. So everything after that, because they don't have a lead 1. This is not a lead 1 because it's not in a separate row. So we need a T and an R. So write that out. X plus Y plus 2Z equals 0. So we're going to say Y is T and Z is R. So X is minus Y minus 2Z. So X is minus T minus 2R. So our parametric equation in our vector form is what? We have a T and we have an R. So T, negative 1T, 1, 0. R, negative 2, 0, 1. So we would say our eigenspace you just write all of that. T and R are real numbers. And what would be one eigenvector? One or the other. Each of them, because you could say T is 0 and R is 1. Or you could say R is 0 and T is 1, so either. Or you could say they're both 1 and add them together, right? Or any other linear combination, picking T's and R's to be any number, you add them together. So there's lots of eigenvectors, but these individually are eigenvectors. Or any linear combination, if we add them together, that would also be an eigenvector, and they'll all work. All right, so that was for lambda is -3. You still have to do the same thing for lambda is 1. So I've got my a minus lambda here. We're going to plug 1 in and do the same thing. I'm just going to rewrite it. Okay, so lambda is, it was positive 1? Yeah. All right, so if we plug 1 in, this one doesn't look right. Did I get all the numbers right before I continue? Yep.
Well, at least I agree with the numbers you got.
What's that?
I said, or at least I agree with the numbers that you got.
Yeah, that's good. So, do we need a second opinion?
Same number you already got.
Okay, there. 2 people agree. All right, so let's row reduce it. So this one I can't jump to the answer, but so row 1 is row 1 divided by 4. So this is a 4 already, so I can just do the zeros from here. So row 2, this 4 needs to be a negative. And row 3 is a negative, so I could just add them. So row 1 plus row 3. All right, so if we do those, and 0, 4, 4, 0. Okay, so, and now I'm feeling more confident that they're right, because you can see that we're going to get a row of zeros. Do you see it? Because row 2 and row 3 are now multiples of each other. So now it will happen. So when you're doing 2 by 2s, you see it always right away, because there's only 2 rows. They have to be multiples of each other. But with R3, we don't necessarily see it right away, because just one of them has to be a multiple of the other to get infinitely many solutions. So our next steps here would be to make this into a 1, and then make zeros above and below. So we made our 1, and we make our zeros. So the first one's in row 1, that's a positive 2, so the 1 would need to be a negative 2. Negative 2, row 2, plus row 1. And row 3, that's a 4, so the 1 needs to be a negative 4. Row 2, plus row 3. And we end up with this. So our lead, we're done, because we made a 1, zeros, 1, zeros, and there's nowhere to make a 1 here. So so we stop. This is in REF. This is a lead. This is also a lead. And then we've got a free. So we're going to say Z is T. Write it out. X plus 2Z equals 0. Y plus Z equals 0. And Z is T. So X is minus 2T. Y is minus T. And Z is T. Just moving them to the other side and putting the T in. Minus 2, minus 1, 1. Okay. Okay, so we'll stop here and we'll go to the next section, which involves doing this all and then another step after. So, yeah, we'll take a break.